Cosmology Supplement 8, Critical Energy Density and Solving the Friedmann Equation. Hello, welcome to this short supplement on critical energy density and solving the Friedmann equation for the Expansion of the Universe course. The lecture script is available at a link given in the description of this video. Section 1, Critical Energy Density. In Main Course Section 10, we covered the Friedmann equation with scale factor dependence. We are ignoring cosmic inflation in this video. Let's rewrite Friedmann's equation with a total energy density being a function of time. If we set curvature kappa to 0, we find a critical energy density, subscript c, for a flat universe from the Hubble parameter, both as functions of time. If the energy density equals the critical energy density, then curvature is flat for all time. If the Hubble constant is 68 km per second per megaparsec, then the present critical energy density is 4,829 million electron volts per cubic meter, or 5.15 proton rest mass energy equivalents per cubic meter. Section 2, Density Parameter Form of the Friedmann Equation. Now we define the dimensionless density parameter omega as energy density divided by critical energy density. And this is the value now, today. We divide Friedmann's equation by the Hubble parameter squared and rearrange to get this new form. Now we set time to now with scale factor 1 and rearrange to get this equation. By determining or assessing omega sub 0, cosmologists would know whether the curvature kappa is 0, plus 1, or minus 1. And with the Hubble distance, you get the curvature, the radius of curvature, r sub 0. Experimentally, omega sub 0 appears to be in the range 0.995 to 1.005, with our universe close to flat. Perhaps exactly flat, but positive or negative curvature with a radius of curvature at least 14 times the size of the Hubble distance cannot be ruled out presently. Section 3, Solving for Scale Factor as a Function of Time. Let's rearrange to get the following equation. Now we divide by h sub 0 squared. Now we split the energy density into radiation, matter, and cosmological constant portions with their scale factor dependences. For simplicity, we will assume dark energy density is constant, W equals minus 1, though we could include the W dependence if we wish. Now we define dimensionless density parameters for radiation, matter, and dark energy. Now we turn the Hubble parameter back into a dot divided by a, and we multiply both sides by a squared. Now we take the positive square root, re-express a dot as dA dt, and multiply both sides by dt. Now we move the square root to the left-hand side, exchange sides, and we integrate both sides from time 0, at which the scale factor is 0, to some scale factor of interest for which we want to know the time. In this equation, we've assumed constant dark energy density and no cosmic inflation. This integral can be integrated numerically given the experimentally determined parameters here, which we covered in the main course. The current standard cosmological model dimensionless density parameters are 0.689 for constant dark energy, 0.311 for matter, and 9.1 by 10 to the minus fifth for radiation. We are within 0.005 of flatness, and the Hubble time is 14.436 billion years. So we would pick some scale factor A that we were interested in. We would integrate this up to that value of A, and this would give us a time, and that would be the time at which the universe had that scale factor. We did not need to assume constant dark energy density in the derivation of this equation. We could have included the scale factor dependence for W not equal minus 1. The integral would still be integrable numerically. The integral can also be solved algebraically for two useful cases, assuming flatness and constant dark energy density. The first case is radiation plus matter, with dark energy density being negligible, and a flat universe. This constant ARM is the scale factor at which radiation gives way to matter. We covered that in the main course. This is the algebraic expression. This gives time since the Big Bang, or the end of cosmic inflation, as a function of scale factor when dark energy density is insignificant. This equation is useful for time being less than 1.35 billion years after the Big Bang. And this equation has a subcase when radiation dominated matter in the early universe. In the radiation-dominated period, scale factor is proportional to the square root of time with this proportionality factor. The scale factor was about 2 times 10 to the minus 10th at 1 second after the Big Bang. The second important case is matter plus lambda, constant dark energy density, when radiation density is insignificant. So for time after 1.35 billion years. This gives the time since the Big Bang as a function of scale factor when radiation energy density is insignificant. This formula gives the same time as the radiation plus matter formula at scale factor 0.183294. Alternatively, we could switch between formulas around scale factor 0.1111 redshift z equals 8, at which radiation energy density and dark energy density are each 0.3% of matter energy density, around 0.64 billion years, so maximum matter domination. In the future, matter energy density will be insignificant, and we will have exponential expansion in our big chill future, assuming constant dark energy density. Starting a few billion years from now, the scale factor will increase exponentially, increasing by a factor of 10 every 40 billion years. Big chill. Every 12 billion years, the scale factor will double. This will be a 5.9% increase every billion years. Here is a graph of the scale factor versus time from the main course, assuming flatness and constant dark energy density. See Main Course Section 14 for a description. The main course also gives graphs of the scale factor in the early universe and for big chill and big rip futures.